Welcome to SOFiSTiK online documentation. In this video, we'll cover the second step of the general workflow for seismic nonlinear time history analysis. We'll demonstrate how to perform a nonlinear time history analysis with prescribed base acceleration in the x direction. We start with the linear static analysis to verify that the normal force levels using during the plastic hinge definition is correct. The analysis includes the quasi-permanent dead load from the pier and the superstructure. These are combined into a single load case number 3, which we generate using the combined characteristic loads task. Once calculated, we can access the normal force level via the graphic module and by examining the diagrams of the load case number 3. From the results, we see that the normal force level is 5,550 kilonewtons, which matches the force we used when generating the moment rotation workflow in the plastic hinge task. Before proceeding to the nonlinear time history analysis, we conduct dynamic eigenmode analysis to determine the structure's natural frequencies. These frequencies are required to set up the Rayleigh damping later on in our time integration. To account for the material degradation during seismic loading, we apply an effective stiffness factor obtained from the cross-sectional analysis in the plastic hinge task. This factor was found to be 18%, as we can see from the report of the plastic hinge task. We determined the eigenfrequencies in the dynamic eigenmodes task. Here we select a maximum number of eigenmodes 20 with the result load case base number of 300. In the primary group, we activate 100% of all dynamic effects for all groups. In the secondary group, we reduce the shear and bending stiffness of the columns to 18% by applying the aforementioned effective stiffness factor. We include the superstructure as an additional mass by converting load case number 1 into mass. Moreover, to filter out irrelevant modes for the x direction, we only consider modes contributing 98% of the mass. Once complete, we visualize the modes in the viewer. The first mode resulted in a natural frequency of 0.78 Hz. The second mode is 12.49 Hz. We will use both of these modes to define the Rayleigh damping in the dynamic time history analysis. Next, we define the base acceleration using Centro earthquake data as the first step of the nonlinear time history analysis. This data is publicly available and is imported into the SOFiSTiK as a time function block that includes both time and acceleration values. The time is defined into seconds, and the acceleration is in units of g, where g is a gravitational acceleration. The data is transformed into a base excitation using SOFI load. We assign load case 100 and use the ACCE command with the node number 0 that activates base acceleration and the excitation type set to Modal. The earthquake acts in x direction, and we apply a factor of 1.4 along with the scaling factor of 9.81, which represents the ground acceleration. This converts the data into absolute unit. The predefined Centro function is imported through func using our predefined block Centro NS. After the computation, we can visualize the time function and verify its amplitude in the SOFI Plus report. Before starting the dynamic analysis, we compute the initial loading state due to dead load to avoid spurious dynamic effects caused by the instantaneous application of the dead load in the analysis. This is done in fair bench using the task fair, which stands for finite element analysis, where we activate both physical and geometrical nonlinearity of second-order theory. As assigned during modeling, the physical nonlinearity is concentrated into the plastic hinges. This is specified through the E-type IHNG. We reduced the shear and bending stiffness of the columns to 18%, which is consistent with the previous steps. We define the load case 200, which includes the self-weight and also copies the load case number 1 of the superstructure load. Once the analysis is run, we can visualize the results. We now perform the nonlinear time history analysis in fair bench. We again use the fair task with physical and geometrical nonlinearities activated. The same group settings apply as for the initial loading state, where we include the factor of 18% to account for the material degradation in the columns. But here we also include Rayleigh damping, with a damping ratio of 5% calibrated at the first and the second natural frequencies. We account for the initial loading state from the previous step using the PLC command. In the load case of the dynamic time history, that is load case 2000, we activate the self-weight and copy the superstructure load from the initial loading state, as well as the base excitation from load case 100. The time history analysis is activated through the step command. We use Newmark time integration and running the analysis for 20 seconds with a 0.02 time step, matching the time step of the earthquake record. Results are stored every step for detailed analysis. For larger models, storing results less frequently may speed up the computation. We control the adaptive time stepping using the FLDT command. This helps manage the time resolution during highly nonlinear behavior and improves convergence stability. We can specify access to response time history using the hist command for preliminary assessment of the analysis. In our case, we use the hist command to look at the moments at both ends of the columns to monitor the plastic hinge behavior and the displacements at the center of the header beam. We now run the analysis, and we can monitor the output of the solver as specified through the echo step command. Once the analysis is complete, we can animate the deformation in the viewer by stepping through the time increments. The report provides key information. The task description summarizes the setup of the analysis. This includes useful tables, such as the numerical time integration settings, convergence criteria, as well as the number and position of the plastic hinges and their work laws. This can be used to verify our input. Moreover, we have a plot of the hysteretic behavior of the plastic hinge under fictitious cyclic loading. This illustrates the cyclic response of the hinges as previously discussed during the definition in the plastic hinge task. The results section provides the output of the analysis. In the first table, we can see that the time integration finished successfully, reaching the specified convergence criteria. We also have a performance criteria table indicating whether strain limits were exceeded and in which material and hinges. In our example, performance level 3, or fully operational, was exceeded at the hinge at the start of the beam 20,023, where the reinforcement, material number 2, reached 10 per mil strain. The time history of this element also shows that the performance limit 3 was reached at 3.1 seconds. Moreover, small plateaus in the moment response suggest yielding, indicating that the moment capacity of the hinge was exceeded during the analysis. We can also observe similar behavior in other hinges. In the next video, we'll briefly discuss the structural performance based on these results. Thank you for your attention.